Hey everyone, Katrina here, and today I'm going to teach you all about horizontal asymptotes. Please subscribe for more videos like this and make sure to watch to the end to see the full example unfold. So horizontal asymptotes are always a bit of a mystery when we're looking at rational functions. And today I'm going to show you 3 cases, and it's going to be foolproof so that no matter what function you have, you can find its horizontal asymptote. So essentially the question that we have to ask is, what happens to our function as x approaches infinity? So if you understand calculus and have some background in limits, you can also see this as a limit. So you can look at this in particular, like what is the limit of f of x as x approaches infinity? So essentially, if we just have a horizontal asymptote, which is a constant function in a certain case, as x approaches infinity, our f of x is eventually going to approach some constant value. So we're pretty much looking at what is the end behavior of the function. So we don't really care what happens like in the meantime when it comes to asymptotes. We're looking at as x approaches infinity or negative infinity in some cases, what is the function going to approach? So in our more basic cases, it will approach a constant value, but stay tuned because in this video, I'm going to show you some interesting and new cases and that involve x approaching a function instead of just a constant. So make sure to keep watching to see that case unfold. Okay, that's enough background. Let's dive in. So in general, we can consider this some rational function in this form. So we have f of x equals to a times x to the power of n plus b, all divided by c times x to the power of m plus d. So we can kind of view this as like a polynomial divided by a polynomial. So when you first started looking at advanced functions, you learn about the properties of polynomials. So now we're kind of stacking these polynomials essentially and using them to create a rational function which has new properties of its own. So let's go ahead and dive into the 3 cases of the different types of horizontal asymptotes that you can get. So again, make sure that you're using this general form over here because I'm going to be referring to these coefficients and these orders over here. So for case number 1, we're considering if our if our power n is less than our power of m. So that means the degree of the numerator is less than the degree of the denominator. When we have this case, then that means that our horizontal asymptote is going to be at y equals to 0. So that's great. Immediately, if you can recognize that the degree on the top is less than the degree on the bottom, then your horizontal asymptote is a very simple case. It's a constant function, and in particular at y equals to 0. So I'm going to show you an example for this case over here. So say we have y equals to 1 over x plus 2. And remember, when we're doing these questions, we're asking us what happens as x approaches infinity. So as x approaches infinity, what is y approaching? This is like an end behavior analysis. So if you know limits, essentially what you do is you plug in the value that x is approaching, and I say quote unquote plug in because it's not, you can't actually plug in infinity because infinity is a concept in math and not a number. But for the sake of this, we're going to look at what happens when infinity exists within our function. So in that case, we can look at it like this. We would have 1 over some infinity plus 2. So whenever we're doing this type of analysis, immediately you want to get rid of any constant value because it's going to be irrelevant next to infinity. If infinity is already infinitely large, what is something infinitely large plus 2? That doesn't really make sense. So the 2 here doesn't really play a role anymore. So we can get rid of the 2. So essentially then what we're looking at is some situation where we have 1 over infinity. And understanding fractions, if you have a small number over a very large number, your whole number, so the whole thing, is going to go to 0, right? Look at it this way. If you have like 1 over 10, 1 over 100, 1 over 1,000, your number is getting smaller and smaller. Here it's 0.1, 0.01, 0.001. So this number is tending towards 0. So that means if you have 1 over infinity, then that whole fraction is going to tend towards 0. So then that means that if we're looking at this in limit form, the limit as x approaches infinity of 1 over x plus 2 is going to equal to, is going to equal to 0. And since that equals to 0, therefore, as x approaches infinity, y approaches 0, and then you can say, therefore, your horizontal asymptote is at y equals to 0. So that's a bit of like a proof that kind of shows us why our horizontal asymptote is at y equals to 0 when the degree on the top is less than the degree on the bottom. Because when you're essentially plugging in that infinity, if your bottom's bigger than your top, it's always going to overpower your function and it's going to win in that case. And then when it wins, that means that it's going to be so large and then your whole number is going to tend towards 0. Okay, so that is our first case, which is nice and easy. Our second case is also very friendly. So let's look at that. So case 2 is if n equals to m, and remember from our function right over here, these are our, the degree that we're looking at. So if the degree on the top is equal to the degree on the bottom. So if n equals to m, then our horizontal asymptote is at y equals to a over c. And again, let's look at what a over c is. A is simply our coefficient on the numerator, and c is our coefficient on our leading coefficient on our denominator. So when they're equal, we just take the fraction of the coefficients. So let's look at an example for that. So here, what if we have y equals to 2x divided by 3x minus 1? And again, like before, we're asking as x approaches infinity, what is y approaching? So in this case, we can again look at the limit definition. So we're looking at the limit as x approaches infinity of y, which is 2x over 3x minus 1. So we're going to do the same thing before and quote-unquote sub in infinity, because infinity is not a number. That's why this is going in quotes, so we can get a general feel for this. And like I said before, what is a constant next to infinity? Subtracting 1 from infinity isn't going to do anything. So we're going to do the same thing before and cross out any constant values. So as a result, what does that give us? Now we have the situation of 2x over 3x, and we're going to sub in the infinity. So we have like 2 times infinity over 3 times infinity. And in this case, well, since you have the number on the numerator and the denominator, that means they simply cancel out. So then what are you left with? You're just left with 2 over 3. So then that means as x approaches infinity, that means y is just going to be approaching this value over here, 2 over 3. So that means our limit equals 2 over 3. And again, this is a constant value. So if you think of some plot that you have, 2 over 3 is just a value that we would have. This is, let's say this is 1. At this point, 2 over 3 would be found just below 1. So you'd have our horizontal asymptote here in green. So that means as x is going towards infinity, then our function is going to be hugging this line. And I don't think I mentioned, but the definition for horizontal asymptote is a line in which the function does not touch, but it gets very, very close to. So that's why the definitions of limits and asymptotes play a role very hand in hand, because they're both kind of these concepts where your function's trying to get infinitely close to something without actually ever getting there. Okay, so that is our case number 2. And now let's explore case number 3. So you'll have to hang in with me here because it gets just a little bit complicated, but I promise we'll make sure we go through it in an easy way. So case number 3 is if n, remember the power on your numerator, is larger than the power on your denominator. So n is bigger than m. What happens then? So I'm going to show a little example to just allow you to wrap your head around what this means. So what if we have y equals to, x cubed plus x minus 1 over x plus 5. So we can see right away that 3 is bigger than 1. So remember, if there's no power explicitly stated, that means that it's a power of 1. So we have that. So 3 is bigger than 1, therefore n is bigger than m. What happens? Okay, so like we had in all our previous examples, we don't care about the constants. They're irrelevant in the eyes of infinity because we're still looking at what happens as x approaches infinity. What is y going to be approaching? So now let's just go ahead and kind of simplify this expression now that we've gotten rid of our constants. So we have x cubed plus x over x. And now we can factor this. So if we factor out an x from the numerator, we're left with x squared plus 1, and then our denominator is x. Well, now that we've factored an x and it's on the top and bottom, it can cancel out. So what are we left with? We're left with x squared plus 1. Now let's go ahead and kind of evaluate the limit of that. So we're looking at the limit as x approaches infinity of x squared plus 1. And we're going to do that same thing where we're going to quote unquote sub in infinity and see how our function behaves. So if we sub in infinity, we get some term infinity squared plus 1, and like I said, the constants don't matter, but we have this infinity squared. So what does that mean? Well, that's telling us that as x is approaching infinity, y is also approaching infinity. And the question that we want to answer, this is very important, is how. So we know that as x is approaching infinity, y is approaching infinity. But how our function f of x or y gets to infinity is what we want to know. Gets to infinity is the big question. I just want to write that down so you have that in your notes. So again, we see that as x goes to infinity, y is also approaching infinity. But we want to know how our function is getting to infinity. What is its trajectory? We want to know what is its path. How is it getting there? So previously, we would see that as x approached infinity, y would either approach 0 or some constant value. It was a constant function, so it was really easy to wrap your head around the end behavior of that function. But in this case, we know that y is going to get infinitely large, but we want to know how it's getting to infinity. Is it following a linear path? Is it following a quadratic path, an exponential path? We want to figure that out. And that's what we're going to do for case 3. So I'm going to give you now a step-by-step approach that you can follow every time in order to figure this out. So let's go through this. So we're going to do case 3 explained. So again, this is when n is bigger than m. Okay, so we want to determine the behavior of the function. So that is the big thing here. Like we said, we want to know the behavior, we want to know the path that it takes as y approaches infinity. So that is what we're trying to answer. So let's go through and do kind of a step-by-step explanation of how we can figure this out. So the first thing that you're going to have to do is now reference our previous skills that we've learned. So we actually want to divide the numerator by the denominator. Okay, so let's see what skills we need there. So we're going to consider an example to help us through this. So what if we have f of x equals to x squared minus x minus 2 over x minus 5. So again, we can see her degree at the top is bigger than the degree on the bottom. So we want to divide the numerator by the denominator. So again, we have some polynomial here and we have some other polynomial here. So what do we have to do if we're dividing a polynomial by another one? We have to use polynomial long division. Or what's the shortcut to that? We can use synthetic division. So I have a few videos up on synthetic division already, so make sure that you check those out if you need a bit more like background on this skill. So we're dividing, again, this quadratic polynomial by this linear polynomial. Okay, so what we have to do here is, if we're considering this as our bottom, so we have x minus 5, this is what we would call like a factor. So here we don't know if it's a perfect factor because we don't know if the remainder will be 0 or not, but this general term is called a factor. And then this term over here, we call this the d term, is going to be our root. So in this case, x equals to 5 is our root. And how do we get that? We get that by setting our factor equal to 0. So we want our factor equal to 0 and then solve for x. So if we set, I'll just show you that step by step, x minus 5 equals to 0, we're going to do the reverse operations. So then we have x equals to 5. And like I said, that is our root. So what we have to do here is then we're going to take our root and we're going to use that in our synthetic division. So let's write a little synthetic division in this corner. Division. Okay, so what we do is you take that root, like I said, and you're going to put it in your top corner. Then from there, you're going to grab all the coefficients of the polynomial on your numerator. So all the coefficients from up here. So we've got 1, -1, and -2. And then we're going to draw a line. Okay, the first step is you drop the first value and then multiply it up with your root. So we've got 5. And then we have to add down the column. So -1 plus 5 is 4. Again, we're going to multiply that up. 4 times 5 is 20. And then -2 plus 20 equals 18. So in this case, we see that we have a remainder. So 18 over here is our remainder. And then what do we have left? We knock down 1 degree and use these as our coefficients. So we started with degree 2 quadratic, and now we're going to have linear. So that means we're left with 1 times x plus 4. Okay, so now what we have to do is step 2. So this was step 1, divide the numerator by the denominator. Okay, check. We have done that. Now let's go to step number 2. So now what we have to do is we need to rewrite the function using the division algorithm. Sorry, it's a long word. Okay, so the division algorithm tells us the relationship between the dividend, the divisor, the quotient, and the remainder. So we're going to now rewrite our function. So remember, we'll just write out what we had initially. So we have our x squared minus x minus 2 divided by x minus 5. So now we're going to rewrite it using the division algorithm. So over here we have x plus 4. So that, oh my goodness, I say x plus 4 and I write x plus 5. Okay, x plus 4. So that means that this quadratic function here, x squared minus x minus 2, can be rewritten as the multiplication between x plus 4 multiplied by x minus 5. Remember, because we divided by x minus 5, right? Right over here. So x plus 4 minus x minus 5. And then now we had a remainder of 18. So then we have to add our remainder. Okay, So now we've rewritten our function. So now we're actually going to go ahead and pretty much follow the same steps that we had before, where we want to solve the limit as x approaches infinity. So we're going to look at all this. So if we look at this term over here, our remainder term, we can see that as x approaches infinity, this part of the function, we'll just call that y2, is going to approach 0. Just like we saw from case 1, the degree on the numerator is less than the degree on the denominator. And if we look at this part over here, we see that the x minus 5s cancel out, so we're just left with x plus 4. And we can see the same thing. As x goes to infinity, y is going to infinity. But now we know that y is going to infinity following this trajectory. So x plus 4 is a path that it's going to follow. So that is the key information that we wanted to get. So therefore, as x goes to infinity, our function y is tending towards the line x plus 4. So this is called a line, and this can also be called an oblique asymptote. So instead of just having a plain horizontal asymptote that we would have before, we would now call this our oblique asymptote because it's no longer a horizontal line, it's actually a linear function that we are going to be following. And that over there is our horizontal or oblique asymptote. So just a little trick to know kind of what type of trajectory to expect. So here we saw that our n equals to 2 and n equals to 1. So I'll write that. So n equals to 2, m equals to 1. And then since we divided, we subtract the exponents following exponent laws. So n minus m is 2 minus 1, which equals to 1. So then the line or oblique asymptote is degree 1. Say, for example, the degree on the numerator was 3. If n equals to 3 and m equals to 1, we would do the same thing. Subtract 3 minus 1, which equals to 2. Therefore, the new asymptote, I'll just quote-unquote horizontal asymptote, is going to be some quadratic function. So to figure out kind of that shape, you would just subtract the degree from the numerator do the numerator minus the denominator, the degrees, and then that will give you the degree of your new quote-unquote horizontal or oblique or quadratic asymptote that your function is going to be following. So in my next video, I'll do an example showing how we can sketch an entire function using our horizontal asymptote, vertical asymptotes, and other key features such as intercepts, domain, and range to get the full picture. But today was a comprehensive lecture showing you exactly how to find horizontal asymptotes for any type of rational function in the general form I showed above. And you just have to first identify which case your function falls under, and then you can use the following steps that I showed you. If you enjoyed this video, please give it a like and subscribe for more videos. I look forward to hearing from you in the comment section, and I'll see you next time.